Bismillah ar-Rahman ar-Rahim. If you have any questions in the previous lecture, you can ask your questions. I hope all of you can hear me. Any questions in the previous lecture?
सर आपने कहा था कि स्पोर्ट्स का बताऊंगा नेक्स्ट क्लास में।
सपोर्ट्स का, अच्छा ठीक है, ओके बताता हूँ।
प्रैक्टिकल
Anything
ये
else? Okay, let me explain this. You have been seeing such kind of supports in your structure analysis courses. Okay, this is called a hinge support, and this is called a roller support. And you know that hinge can offer horizontal and vertical resistance, but hinge is unable to resist bending moment. Bending moment cannot resist. While roller can only offer vertical resistance, and it cannot offer horizontal resistance, neither it can resist bending moments. Okay? Practically, in reinforced concrete structures, very seldom will you find such kind of supports. However, in steel structures, you can find such kind of supports exactly whose nature will be like the hinge and roller in steel structures. But if we talk about the reinforced concrete structures, in reinforced concrete structures, only the response of a given support will tell us whether this is to be treated as a hinge or roller. So let me give you some examples. You know that the column will be provided with a foundation, okay, like this, and with the foundation, isolated foundation, for example, like this. Okay, so both the columns will be supported on a isolated column footing. Let's say if they are supported on isolated column footing like this one. So in this case, whether okay, and then this pad will be resting on side. You know this. This pad will be resting and on side from all sides. So the load from the beam will be transferred to the column. Okay, and from the column it will go to the footing pad, and from the pad it will be transferred to the ground, and okay, like this. Now the bending moments, whether this pad is able to resist some kind of bending moment or not, it will depend on the size of the pad. If the size is very large, if the size of this pad is very large, then of course it will offer some bending moment resistance, and this can be treated instead of a hinge or roller support as a fixed support. But if it cannot offer any bending moment resistance to the design loads, whenever we say that it cannot resist or it cannot offer resistance, we mean to say that its response to the design load. So for the load for which the structure is being designed, if this pad is unable to offer resistance, if this is unable to offer resistance, then it will be treated as hinge support. Hinge support, because this cannot offer bending moment resistance. And how do we know this, whether this will offer this bending moment resistance or not? This for this we will have to design this support. So how can we do this? For example, after the analysis, in the beginning in your analysis, you assume that it is a fixed support, okay? Because at the beginning you do not know what kind of footing you will provide. Let's say you are assuming in the beginning that this is a fixed support. I will provide a fixed support. Then what are the requirements of fixed support? A fixed support should provide vertical resistance, horizontal resistance, as well as a bend. Vertical resistance means that it should not settle, it should not move down. So vertical resistance ideally will be provided by all kind of support, all kind of foundations, because if there is no soil settlement and if there is no structural failure of the foundation, then it will offer the vertical resistance. Horizontal resistance resistance will depend on many things. Horizontal resistance will depend mainly on the friction between the foundation pad and the side. And normally, this is up to an extent that horizontal resistance is also available. So horizontal and vertical resistance will be available in almost all cases. Okay. So to assume that the support is a hinge support, this is very logical, and in all cases, it to act as a fixed support, then the bending moment resistance will be up by the column and the foundation. The contact point between the column and the foundation. The contact point between the column and foundation shall be, which is design such that, which means that the bending moment resistance means that enough reinforcement shall be provided in this column and the foundation interface, so that there is bending moment. The column should not fail at the interface of the foundation. Okay, so in the like a fixed support, then we should design this, that we should design the support so that it behaves like a fixed support. Okay, so the assumption shall be the assumption in the beginning shall be supported by the design. हेलो,
Yes, sir.
Yes, sir.
अच्छा आप मेरी आवाज सुन सकते हैं अभी?
Yes, sir.
Yes, sir.
जी सर।
Yes, sir.
ओके, सो आज हम अपना लेक्चर नंबर 6 शुरू करते हैं, ठीक है?
All right, sir. So I have a question for start.
You have a question? Please ask question.
Sir, I have seen in a video for simply supported beam.
Weight support?
Simply supported beam.
Okay.
So if you have taken the section from the middle, the main bar will be like for example, 4 bars, and hanger bar will be 2. But if you take a cut on the support, so the hanger will be 4 and main will be 2. In the video, he said that he using it for supporting the share in the middle, not on the support. So how can you explain that?
Okay. You are Ahmad?
Yes, sir.
So you can you repeat your question? There was a beam. You have seen a beam in a video where it was simply supported.
Yeah, it was simple supported beam, and he said because of the
Yeah.
share in the support is the maximum, so the
Simply supported beam, and there were excuse me, there were main reinforcement. By main reinforcement, you mean the flexure reinforcement, longitudinal bars.
yes.
Okay, in longitudinal bars, when there was a section when taken at the midspan of the beam, what did you see over there?
The main bar were 4 and the
Okay.
hanger bar were 2.
Okay.
But
The top bars were 2 bars.
yes.
Okay, and when you saw a support section near the support. So what did you see over there?
Yeah, the upper bars became 4 and the main bar became 2 because he took turn for the main, 2 of the main bars by 45 degrees to support the upper bars.
Okay, and okay.
And he's executed because he said that the share in the support is the maximum, so it need to be supported.
No, the flexure reinforcement has nothing to do with the shear reinforcement. You have to clear this concept, okay? The flexure reinforcement, if there are 4 bars in the midspan, this is very obvious, very clear, and very logical that midspan will be subjected to maximum bending moment. Okay, so it should have 4 bars. That is correct. But why these bars are curtailed, reduced towards the support? Again, this is very logical because positive bending moments are very small near the supports. If you draw a bending moment diagram, you can see the screen. Ahmad, can you see the screen?
No, sir.
No, sir.
Okay, can't see the screen.
Still, there is no screen there.
Okay.
So there is screen, but you just you are presenting the classroom.
Okay, now we are doing. No, don't worry. Okay, can you see the screen now?
Yeah, yes, it,
Ahmad, can you?
yeah, it's
Huh?
visible.
Okay, okay. Okay. You can see the screen now, huh?
Yes,
Yes,
sir.
sir. अभी ठीक है.
Okay. So you mean that there was a beam like this, okay, resting on, you say that it was simply supported, but I don't think it was simply supported. It might have been continuous supports like this, maybe a support like this here, and the beam was continuous past this support, okay, like this. So the bending moment diagram for this, the bending moment diagram for this will be like this. Positive bending moment and negative bending moment. Okay.
Yes,
You can-
yes,
okay. So you can see that near the support, the positive bending moment becomes 0, and the negative bending moment is
reduced. Yes.
negative bending moment is introduced. So if there are 4 bars here, 4 bars here, you can curtail some of these bars or reduce some of these bars near the supports. You can make 4 bars 2 bars. You can cut 2 bars so that you bring some economy to the project. Okay, and then because there is negative bending moment, so 4 bars will be maybe required here instead of 2 bars here in this location. Okay, Ahmad?
Yes, sir. Now it's clear because of the moment.
Yeah,
Okay.
because of the moment.
Thank you, sir.
Okay, anything else?
No, sir. Go further.
Okay, okay. So let's start the today's lecture. Okay, I hope all of you can see the screen.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. In today's lecture, we are going to design slab beams, girder, columns, and footings of a 90 by 60 feet hull. And there is a requirement that minimum obstruction to mobility inside the hull requires that only 2 columns can be allowed inside the hull. In the previous 2 design example cases, which we were discussing in the previous lectures, we allowed no columns inside the hull. But this time, minimum obstruction to mobility inside the hull requires that only 2 columns can be allowed. So if 2 columns are allowed, we will take advantage of this and we'll place 2 columns symmetrically. We'll try to place these 2 columns symmetrically in this hull. Okay, like this. If you remember the previous 2 cases, in the beginning, in the first case, in the 90 by 60 feet hull, all the beams and slab were supported on brick masonry wall, if you remember. Okay, and then in the second option, the columns were provided under every beam on both sides, and then the walls were acting just like non-load bearing walls. Okay, in the first case, all the load from the slab and the beams was transferred to walls, and the loads were acting as load bearing walls. In the second option, in the previous lecture, the load was transferred from beams to the columns and from columns to the foundation, and beams the walls were acting only as non-load bearing wall system, taking no part in load sharing. This is a third option wherein this is basically an amendment to the first option, where brick masonry walls were provided on all sides. Okay, but the only change that we have done to the first option is that we have provided 2 columns inside this hull. I hope you understand this now.
Yes, sir.
Okay, and another change that we have done in this option, that we have provided a beam along the 90 feet side of this hull here. This is beam, and this beam we call as girder. This beam we call as girder, and girder is from the structural point of view, girder is not different from beam. Even from shape point of view, it is not different from beam. It is just like a beam, but it is a terminology that whenever 1 or more beams are supported by another beam, which is relatively stiffer than that supported beam, then that beam is called as girder. So if you look at this figure, this is a beam, and this beam is supporting these two beams. So this beam, which is supporting these two beams, is named as girder, though from structural point of view, it is the same as beam. So there is no difference from structural point of view. It is only just to differentiate that this beam is supporting this beam is stiffer. This beam is stiffer and stronger than these two beams, and this beam is called as girder because it is supporting two other beams. Okay. The spacing between the beams is being kept the same as of the option 1, 10 feet center to center. Okay, so everything remained the same, except that now these beams, 60 feet long beams, are supported at their mid spans. Okay, here in these locations. Okay, so every 60 feet beam is being divided into two spans, 30 feet each. 30 feet each. Okay, and at two locations, these beams have been supported on columns, and at all other locations, the beam has been supported on girder. Okay, the walls are 18-inch thick. In a 3D view, it will look like this. If you want to see a 3D view of this, just to clarify your imagination, so it will look like this. I hope you can see this picture very well.
Yes, sir.
We have removed a wall from this side. Okay. Okay, we have removed a wall from this side. So there is a wall here, but just to see inside of this wall, we have removed this wall. This wall is again a brick masonry wall, a load-bearing wall. Now, if you look at this beam we call as girder. The depth of this girder is generally more than the depth of the supporting beams. Okay, this beam depth is less than this beam. So this beam we call as girder because this is stiffer than this. Otherwise, this beam will not be able to support these beams. So this is, if you want to draw the section of a girder, you can draw section of the girder. Girder is supported on one side on a wall. So wall can be treated as hinge or roller support. On the other side also it is hinge or roller. And on two intermediate points, it is being supported on columns. Okay, if you want to draw a section of a beam, so beam is supported on one side on a wall, another side on a wall, and at the midspan either on a girder or on a column. Now let's look at the load transfer mechanism, how the loads are transferred. Let's look at this animation. This is a very useful animation. On top, you can also see how the beams and girders are arranged, just to clarify the concepts. Okay, you can see this is girder is running. Girder is supported on this side on a wall, this side also on a wall. Okay, intermediate supports on columns. Beam supported on masonry wall here on this side and masonry wall here on this side. Okay. You know that in the load transfer mechanism, the slab load will be transferred to beams, as you have seen in the previous cases, option 1 and option 2. Okay, you've seen in the previous cases of option 1 and option 2 that the load is transferred to the beams. The load is transferred from the slab to the beam. Half the load on one side of the beam and half the load on the other side of the beam from the slab is taken. Okay, so if we look at this animation now, I hope it will be clear to all of you. This is the animation. So half the load is coming from one side of the slab, half the load is coming from other side of the slab, like this. Okay. Now this load will be transferred then to, okay, this is a small portion on the girder. will be transferred to the girder from the slab. So the slab, the beam will be idealized like this. This process is called idealization, as I was discussing in the beginning, as a response to one of your questions, that how these beams are idealized now. You have seen that first the load mechanism is idealized, okay, that the load will be transferred to the beam from the slab, half of the slab on one side and half of the slab on the other side. And that load will be calculated as a uniformly distributed load. And then this uniformly distributed load will be applied on the beam with the relevant supports. Now this support, which is a wall support, this wall support can be treated as hinge support. Why this can be treated as hinge support? Because the connection between the wall and the beam is not monolithic and is not capable of resisting bending moment. It's not capable of resisting bending moment. How can you imagine this? For example, if you remove one of the wall, okay, so then fixed support, you know that fixed support should be like this. Even one support is capable of resisting the bending moments and the beam will not collapse. However, in the case of a wall, if this is a masonry wall, and if you construct a beam on top of the masonry wall, this wall is not going to resist the bending moment and the beam will collapse. The beam will not be stable because the support is not a fixed support. However, if you construct this of a reinforced concrete wall and you extend reinforcement into this, the beam reinforcement is extended into the reinforced concrete wall, then there is a possibility that this support will act as a fixed support and the beam will not collapse. So a beam resting on a masonry wall cannot be treated as fixed support. It must be treated either as a hinge or roller support. Okay, so this is treated as hinge support, this support. The intermediate support, which is now a beam girder connection. A beam girder connection can be treated as a hinge support or a roller support. The other support can also be true support. Both are correct. Okay, but why have we assigned? Now, why have we idealized these two supports as roller support instead of idealizing them as hinge support? Because in the first case, we idealized this as a hinge support, the second is a roller, and the third is a roller. There is a reason to this. Though from the analysis point of view, there will be no difference if you analyze this system with a hinge support at the midspan and hinge support at the extreme edge of the other wall. From the structural point of view, there will be no difference because the bending moment is not resisted at the extreme ends, and there will be, because there is no horizontal load, so there will be no horizontal reaction. There will be vertical reaction and a bending moment here, negative bending moment at the support. There will be zero bending moment, and zero bending moment here. Then why have we idealized these two supports as roller and one of the supports as hinge? Let's discuss it like this. If we idealize all of them as hinge supports, this as hinge supports and also this as hinge support, what will happen? If you load this beam, then physically, practically, not in this idealized model, idealized beam model. Physically, practically, what will happen? Look at this 3D structure. When this beam is loaded from one end to another end, how will it respond to this load? The beam will come down. You know that the beam will come down like this, okay, and then it will. It cannot come down here at the support at the location where the beam is supported on girder. Then again, it will come down, and the elastic curve will be like this. The elastic curve for this beam will be like this. Can you see this elastic curve that I have drawn on 3D?
Sir. Yes,
Okay.
sir.
Okay, so idealization of this extreme end, when this is a hinge support, this is clear. But if we also idealize the intermediate support as hinge support, then you should mind that the idealized model should represent as closely as possible the behavior of the physical structure. Okay, the idealized model, which is this one, this is the idealized model, idealized beam model. This should present the behavior of the physical structure as closely as possible. So what is the physical or actual behavior of the structure? The beam will come down, and the beam cannot come down at this point. Okay, and there will be slight rotation also at this location, slight rotation of this this location where the beam is supported on girders. But if we assign a hinge support to this location, a hinge support, then a hinge support, you know that the hinge support cannot move. Okay, the roller can move a little bit. The roller will move. It will be possible for the roller to move horizontally. So practically there will be slight horizontal movement at this support, a slight horizontal movement at this support, at the intermediate support. So in order to represent this, horizontal movement, we assign this intermediate support. We idealize this intermediate support as roller support instead of hinge support. In order to for this horizontal movement. Okay, if the support is idealized as hinge, so the hinge will be firmly connected to the beam point, and the horizontal movement of the beam at this location, slight horizontal movement, there will be slight horizontal movement above the girder here at the intermediate support. This will be restricted, so it will not represent the actual behavior of the structure. Although from the structural point of view, from the analysis point of view, there will be no difference. Now coming to the last support. The last support is treated as roller support because if there is a thermal movement, due to temperature increase, so because you know that the beam is having some reinforcement, flexure reinforcement, longitudinal bar. So this longitudinal reinforcement due to thermal movement will push these walls in the horizontal direction in this way, and there will be slight movement at both ends due to this thermal movements. And you know that hinge support cannot move. Okay, so hinge support will offer this resistance to this thermal movement. However, from practical point of view, we know that whenever there is a thermal movement, this thermal movement cannot be completely resisted by the walls. Especially when there is a when the beam is supported on the walls, and only friction is responsible. Friction between the beam and the wall is responsible for resisting this thermal movement. Okay, so this will not be possible for this. For this reason, we will provide one of the support is hinge support and the other support is roller support. Okay, so that this support can move. Ideally speaking, we should have provided both sides as roller supports. But if we provide both supports as roller support, then the structure will become unstable. A slight horizontal movement in the structure, in the numerical model, will cause movement of this the whole beam. So in order to prevent this whole beam from horizontal movement, we will provide hinge support on one side and roller support on the other side. And the total horizontal movement will be accommodated on one side, and then we will divide this horizontal movement on both ends of the beam in order to take care of this horizontal movement. So this is some kind of explanation to this idealization. I hope you would have understood a little bit of this, though it is a difficult concept to understand. As I said earlier, if you are interested more in such kind of concepts, you better go through one of my MSc lectures, which is available on the website, idealization of the physical structural models. So it will further enhance your understanding of idealization. Anyway, the idealization is now like this, that we have provided hinge support on one side and roller support on the other side of the wall, and also intermediate support to the wall. So now, idealization of the girder. The girder idealization is like this. a small portion of the slab, which is left, small portion of the girder self weight will act as a UDL on the girder, and the beam, half the beam from one side and half the beam of another side will be lumped as a point load on the girder. Or in other words, the reaction which is coming on the girder will be acting basically as a point load on the girder. So these two beams are supported by girders. This will act as a point load on the girder, 3-span girder, and the self weight of the structure and small part of the slab will be acting as a uniformly distributed load on the girder. So this idealization of the girder will look like this. Okay, now let's start our designing steps. First of all, the slab design. The slab design will not be different from what we have already designed because everything remains the same. It is a one-way slab, although in the previous case the ratio was 90 by 60 by 10, 6. But here the ratio is 30 by 10. Still, it is a one-way slab. The end span and the interior span, everything remains the same. So the slab reinforcement and everything will remain the same. We'll just repeat the process quickly. Slab 6-inch assumption and so the slab reinforcement remains the same without any change. These are slab loads, which again remain the same. Okay, bending moments.
Sir, the assumption of height of the slab is usually 6 inches, or according to what?
Yeah, it depends on the span length of the slab, In all the cases that we've discussed so far, the slab span length was 10 feet. So for 10 to 12 feet, it is good to assume slab thickness equal to 6 inch.
All right, sir.
Okay, for one-way slabs. If it is more than this, if you remember, in the last lecture we did a case study, and in the case study, when the slab length increased to 15 feet and 20 feet, then the thickness of the slab also increased up to 8 and 9 and 10 inch. If you remember. So it depends on the slab length.
Oh, okay. That's
okay.
Yes, sir.
This is the reinforcement in the slab, which is the same. We're just repeating the same steps. Finally, the end result is the same as it was in the previous two options, 1 and 2. 3 by 8 inch bar at the rate of 9 inch center to center, both ways, main reinforcement as well as longitudinal reinforcement in this. Okay. Okay. So now we will discuss the beam design, because slab design we have already discussed 2 times in option 1 and 2. I hope that is clear to all of you. Okay.
Yes, sir.
Okay, let's start the design of beam. This is a 2-span beam now, unlike the previous case, option 1 and 2, where the beam was simply supported single span beam. It is a 2-span beam now. Okay, and we have discussed the idealization of this. So between the supports, the unsupported length of the beam is 2 span. So the span length of the length of one span is 30 feet now. The length of one span from like this. From the interior side of the wall to the center of the girder. This is the girder. Okay, this is girder, 18-inch wide girder. 18-inch wide girder, we assume that the width will be 18 inch. Okay, and from the center of this girder to the interior part of the wall, inner part of the wall, this is 30 feet, because the total interior dimension of the hall is 60 feet. The clear length we can calculate now by deducting 9-inch, which is the girder, half girder width. 30 minus 9-inch is 29.25, and 30 minus 9-inch is 29.25. So the clear span length of the beam is 29.25 feet. Every span is 29.25 feet. We will design 29.25 feet beam instead of designing 30 feet beam now. Okay, this is a beam which is simply supported at the ends and continues at the intermediate support. So the bending moment diagram will be with a positive bending moment and negative bending moment, then a positive and zero. Zero, positive, negative, then again positive of the slab. The same formula will be used. Minimum thickness of the beam is L by 18.5, and all this, if all this is done, then Ln plus depth of the beam is 31.25. Center to center is 30.75. Okay, and after using the ACI equation L by 18.5, we get a value of 15.95, which means that the depth of the beam shall not be less than this. This is the minimum requirement of the ACI code. Although we can always assume depth more than this, but not too more, because if it is much more than the minimum depth, then it will unnecessarily increase the weight of the beam, and it will unnecessarily increase the reinforcement and all other things related to the weight of the beam. Okay, so instead of assuming 16-inch, we assume a 24-inch deep beam, where 6-inch will be embedded inside the slab, and there will be 18-inch hanging part of the beam. 18-inch part will be hanging. If you look at the section of the beam here, so the beam looks like this. The 24-inch depth of the beam means this total depth, which also include part of the slab. 24-inch from this part to this part. So 6-inch is this slab part of the beam, and 18-inch is this hanging. This is called hanging part of the beam, hanging part, or web part. In engineering, we call this web part, and generally, common people working in the field, they call this hanging part of the beam. And in their perception, beam is only this part, which is hanging from the slab. However, you know that beam is also going into the slab, and some part of the slab is also part of the beam. So total depth of the beam will be part of the slab, will be thickness of the slab, and the thickness of the beam below the slab. This is the total depth of the slab, and this is the width of the slab, beam, width of the beam. Okay. Finally, we assume 24-inch deep beam and 12-inch wide beam. How do we assume this 24-inch beam instead of 16-inch? How do we know this? This we have tried to explain in some of our lectures. This depends on many things. This depends on the availability of the formwork in the market, because sometimes, for example, if you want to assume 20-inch instead of 16-inch, let's say you want to assume 20-inch beam. So with 20-inch beam, what will happen? 6-inch part of the beam will be inside the slab, and 14-inch will be hanging, and it will be sometime not easily possible to get hold of 14-inch formwork, 14-inch deep formwork. It will be difficult to find such kind of formwork. The easily available formwork are 18-inch and 15-inch formwork. They are easily available. 14-inch is a art kind of formwork, so it will not be available. So keeping in mind these formwork availability in the market, we will assume a suitable depth of the beam. And the suitable depth of the beam in this case is 24-inch in my opinion. Okay, now calculation, please.
So you have assumed according to your experiences, but as a student, so we need like to have a certain one, but just for learning. When we go to the business one, so on that time we will learn.
Yeah. Okay. So what is your question?
Like just if you give us a certain values, we have to use it in our all problems. Now,
Yeah, as far as from academic point of view, you can assume any depth as long as it is larger than the minimum depth of the ACI. From the academic point of view, it will not make a difference. I am talking about the practical aspect of this assumption, because anything that you design in your design office or in your offices, in your labs, that will be actually constructed. So construction will be done from the practical point of view, the availability of the practical requirements, like the farm work, the people who will be constructing this and all this. So that things must be kept in mind. Otherwise, this will be an exercise, futile exercise. It will never be practically applicable. So these things shall be kept in mind. I know that students cannot appreciate, they cannot realize these practical problem, and that is the reason that I am time and again trying to explain these practical aspects of the design.
okay, so sounds clear. Thank you.
Okay. Okay, load on the beam. Load on the beam coming from the slab, factor load is 0.214 kip per square foot. There is no change in this. 0.214 into 10, 2.14 kip per foot, as we have done in the previous option. However, self weight of the beam will now be reduced. Okay, because in the previous case, option 1, the beam was 60 inch deep. Now the beam is 24 inch deep, where 6 inch part of the 6 inch of the beam is inside the slab, and 18 inch is below the slab. So if you look at this beam, the beam will look like this: 18 inch and 12 inch. 6 inch of this 6 inch is inside the slab. So when we take the center of the one part of the on one side of the beam and center of the slab on the other side of the beam, this also includes this part of the slab. So the slab load shall not be counted twice. Okay, the slab load has already been included in the this part of the beam has already been included in the calculation of the slab load. The remaining part, 18 inch by 12 inch, this is the self weight of the beam. This needs to be calculated now. 12 by 18 and divide by 144 into 0.15. This will give you kip per foot load. Multiply by 1.2 to make this factor load. This will become 0.27 kip per foot. The total load on the beam will become 2.41 kip per foot, which will be assigned as UDL this beam. .41 kip per foot, like this. Now I will ask you to take few minutes and look at this analysis diagram, shear force and bending moment diagram. Please draw these bending moment diagrams and shear force diagram from this slide yourself on your sheet. And then I will ask you to design the beam for flexure first, okay, and then for shear. Okay, I'm sitting here. If you have any question, you can ask your question. But first of all, draw this shear force diagram and bending moment diagram on your sheets. Start working on this. Okay. And after you complete this, the next step will be designing this beam. And so far, we have learned how to design a beam. The only difference in this beam is that this is a continuous beam. You need to design this for negative bending moment, which is 2749 H kip, and a positive bending moment 22.4. This is 22.49 H kip. Since the beam is symmetrical about its midspan, so you need to design only one positive bending moment and one negative bending moment. For negative bending moment, you will have to provide reinforcement as top bars, and positive reinforcement, you will have to provide reinforcement as bottom bars. So you draw the bending moment and shear force diagram for this beam, and then we will go ahead. Okay. Okay. If you have anytime, if you feel you have a question, you can ask your question. Okay. You can stop me and ask your question. Okay, please. Now start drawing the shear force and bending moment diagram. Okay. I will give you 10 minutes to do this and start designing, and then we will discuss the designing steps. Okay.
Hello everyone.
Yes, sir. Yes, sir. एक मिनट सर, ये डायग्राम ना हटाएं।
Hello everyone. वो सर बाहर चले गए, मैं अभी सर कटी इधर बैठा हूँ। अगर किसी को कोई प्रॉब्लम हो, कोई मसला हो, फिर मुझसे पूछ ले।
ये स्क्रीन जरा फुल स्क्रीन करें सर प्लीज, स्लाइड। हेलो सर।
अब स्क्रीन आ रही है फुल?
जी ठीक हो गई है, थैंक यू।
हेलो। हेलो, प्लीज अटेंशन।
Yes, sir.
Yes, sir.
ये दूसरे लेक्चर में ये स्लेब का जो डिजाइन था, इसमें ये इस नेगेटिव बेंडिंग मोमेंट के लिए ये डब्ल्यू एल एन स्क्वायर और ये कोफिशिएंट 1/12 है। इधर समझ आ रही है ना? तो यहाँ पे लेंथ वो 9.5 फीट है और यहाँ पे राइट साइड पे वो 9 फीट है। तो इस सीआई के जो प्रोविजन है वो कहते हैं कि इन दोनों का एवरेज लेंगे और यहाँ पे ये नेगेटिव बेंडिंग मोमेंट यहाँ पे इस तरह आएगा। तो 18.31 और 18.31 ये दोनों एक जैसे आते हैं।
Okay, sir.
थैंक यू।
एक्सक्यूज मी सर, ये डायमेंशन जरा दिखा दिए बीम की।
कौन से बीम?
इसमें जो बीम एनालिसिस है।
ये इस स्लाइड पे जो बीम है?
यस सर।
क्रॉस सेक्शन डायमेंशन?
यस सर, वही।
सही है। ये 12 by 18, 18 इसका वेब पार्ट है और 6 इंच स्लैब है, तो टी बीम वो 12 by 24 बनता है। 6 इंच स्लैब है और 18 इसका वेब पार्ट है। ठीक हो गया?
यस सर, सही है।
Okay, so now you will start discussing the design of this beam. This is the analysis. The design steps are as usual. First of all, for positive bending moment, we will have to calculate the effective width. I hope all of you can hear me now.
Yes, sir.
Okay, so B effective for T beam is minimum of 16 inch of plus BW. Clear span of beam divided by 4 plus BW will create spacing between beam plus BW. This you know from your previous course. The minimum B effective comes out to be 99.75 inch for this beam. Now, in the next step, we have to check that whether this beam is to be designed as rectangular beam or T beam. Okay, we will assume small a equal to depth of the beam, depth of the slab, 6 inch, and then calculate AS. When AS is calculated, MU divided by 5FYD minus A by 2, MU is 2249 positive bending moment. So AS comes out to be 3.47 square inch. We will recalculate A, and A is ASFY divided by 0.85 C prime B. This comes out to be 0.54 inch, much less than the total depth of the slab. So the flange thickness will design this beam as rectangular beam because small a is within the slab depth. So after trials, now you can continue the trials and recalculate AS, and finally, when the values change, no more change, then you can select that value of AS. AS is finally 3 square inch. AS maximum can be calculated. You know the equations for AS max and AS minimum. AS maximum is 5.81 square inch. AS minimum is 1.26 square inch. So AS is within the maximum and minimum range. This is okay according to the ACI code requirements. AS shall be not more than AS max and shall not be less than AS minimum. So then next we have to decide which bar is to be used. Please, if you have any question, you can ask question.
Not just I want to mention that is just second 3.01.
Oh, okay, no problem. 3.01 is okay. So 0 will not make a difference. Okay. Then we have to decide which bar is to be used. So there can be many options. In this particular case, we use number 8 bar, whose area of steel is 0.8 square inch. So we will divide the 3 by 8, and when we divide this, 3.78 bars are required. We will round this to 4 bars, and 4 bars will have an area of 4 into 0.8 square inch, 3.2 square inch. So 3.2 square inch will be the actual area of steel placed inside this bar for positive bending moment. For negative bending moment. Negative bending moment, in negative bending moment, there is no need of calculating effective width because the slab, the effective width is calculated only for positive bending moment because the flange part, which is the slab part, is acting in the positive bending moment. When the midspan of the beam bends down, then the compression part is within the slab, and slab has a larger width as compared to the beam web width, and for this reason we have to calculate the effective width of the beam. The effective width of the beam is basically the width of the slab which is taking part in resisting the compressive force, okay, the compressive force when the beam bends down. And when the beam bends up, in the case of negative bending moment, the whole flange part, which is the slab part, will be subjected to tensile stresses and tensile stresses. You know that concrete is weak in tension, and that part will get cracked, and we need to place reinforcement in that part, okay, in the upper part in the case of negative bending moment. And the compressive force in the bottom part will be basically now within the web width, which is the beam width, BW. So for negative bending moment, we do not calculate B effective. For positive bending moment, we calculate B effective for this reason. Okay. So for negative bending moment, web width is 12 inch. This will be used. MU is known to us from the analysis, 2749 inch kip. Total depth of the beam is 24 inch. Effective D is 21 inch. Let's, in this case, assume small a equal to 0.2D. 4.2, and after trials you will get the area of steel. The area of steel is 4.18 square inch. Finally, still less than the maximum area of steel and more than the minimum area of steel. And if we again use number 8 bars, so number 8 bars, 6 number 8 bars will be finally selected. Okay, and 6 number 8 bars will give us an area 4.8 square inch. 4.8 square inch is much larger than 4.18 square inch, but this is a compulsion because the number of the diameter of the bar available in the market must be taken into consideration while selecting a particular bar. Okay. So number 8 bars, if number 8 bar is to be used, 6 number 8 bar will be required because the value will be actually coming out to be 4. If 5 number 8 bars are used, then 5 into 0.8 will give us an area of 4 square inch. And 4 square inch is less than 4.18 square inch, so we will add another bar and we'll make these bars as 6 number 8 bars. And for shear. This time for shear, we will use this table, which is very simple to be used, and a lot of calculation will be done in the background. We know that from the shear force diagram, the critical shear is 31.03 at the exterior end of the beam and 35.68 at the interior end of the beam. From the calculation WU ln by 2 is 1.15 WU ln by 2. We already noted down the shear force diagram. You can look at the shear force diagram. Phi VC is the capacity of the concrete in shear. Phi 2FC prime BW. Everything is known to us. BWD 2FC prime. This gives us a value of 20.7 kip. 20.7 kip is less than 31.03. So we have to design this beam for shear. Reinforcement is required. Okay, then this is the spacing which is required as per this VU. Spacing required and the exterior end of the beam is 13 inch and the interior is 9 inch. And maximum, according to this 4 equation, 1, 2, 3, and 4. These are 4 options, 1, 2, 3, and 4. The least of this will be taken as the maximum spacing according to the ACI code, 10.5 and 10.5. Since 13 inch is more than 10.5 inch, so 10.5 inch will be selected, but 10.5 inch is more than 9 inch, so 9 inch will be selected in this case. Finally, we will check also phi VS. You know this phi VS, and this check. Finally, what type of stirrups and what spacing shall be provided? We have decided that we will provide number 3 bar with 9 inch center to center spacing throughout, starting at S by 2, 4.5 from the face of the support at both ends. Because the actual requirement is 10.5 and 9 inch. And there is only a difference of 1.5 in between the two values. So in order to simplify our design, we will provide 9 inch spacing throughout the beam, instead of changing the spacing for only this 1.5 inch change. So I will show you before the design of girder how this slab has been detailed. Okay, finally the slab drafting will look like this. If you look at this, at the end we will discuss this once again, but just I wanted to show you how these steps are placed. Okay, the first step is placed at 4.5 inch center to center. 4.5 inch from the, sorry, the first step is placed at 4.5 inch from the face of the wall, and the rest of the steps are placed number 3 at the rate of 9 inch center to center. 9 inch center to center. Throughout. Okay. Now, after the beam design, we will design girder. Okay. As I said earlier, girder is nothing more than a beam. Okay. But this beam is stiffer than the other beams because this stiff beam is going to support other two beams.
जी सर
जी please.
सर नेगेटिव मोमेंट्स जो हमारे पास बाहर आते हैं उसको किस तरह प्रोवाइड करेंगे
बीम में?
हाँ जी सर।
हाँ, बीम में उस डिटेल में थे, मैं आपको दोबारा दिखाता हूँ। This is the positive bending moment. For positive 4 number 8 bars have been provided. Okay, this 4 number 8 bars have been provided. Negative reinforcement 6 number 8 bars have been provided. So you can see 2 lines here. Can you see these 2 lines? This line and the top line, 2 lines. If we take a section BB, so in section BB we'll be able to see positive reinforcement for 4 number 8 bars and all the negative bars. So what we have, negative bars have been provided like this: 4 bars in first layer and 2 bars in another layer. Okay, up to
Yes,
L by 3. L by 3 of this 30 feet beam is 10 feet. So 10 feet from the face of the wall on one side and 10 feet on the other side. We have provided 4 plus 2 bars because we have negative bending moment here. Okay.
जी
But
सर
however, if you take a section at AA, section A, so in section A you will be able to see only 2 number 8 bars, 2 number 8 bars. So which means that these 2 number 8 bars from the first layer and 2 number 8 bars from the second layer have been curtailed here at this location. This bar you can see in the long section that is completely eliminated. This does not go beyond this point, the second layer, which means that these 2 bars which are placed in the second layer does not go beyond this point. Okay.
जी सर
However, this small cut, you can see this small cut in the line. This one, you can see this. This small cut in the line, can you see this?
No, sir.
सर एक्चुअली आपके माउस का पॉइंटर नहीं है इसलिए
That's a point you cannot see. Okay. Now I will show you this on this. Can you see this now?
यस सर
Okay. So this small cut tells us that something has been done to the bars in the first layer. Some bars have been curtailed or cut beyond this point. Okay. The second layer is very clear. At the bars in the second layer, they do not continue beyond this point. Okay. But the first layer, in the first layer, there are 4 bars. So if you take a section now AA, section AA tells us that the 2 bars, these 2 bars
यस सर
have been curtailed beyond this point. So you can't see these 2 bars here in this section AA because we have negative bending moment, maximum negative bending moment in this part. If we draw a negative bending moment diagram, bending moment diagram, it will be like this. I'm sorry, this, no, it should be like this. Like this. Okay, so you have a negative bending moment only in this region. We don't provide negative reinforcement beyond this location. However, just 2 bars to hold these stirrups will be provided from one end to another end. Correct?
ये सर अगर हमारे सर दोनों एंड में हमारे पास फिक्स सपोर्ट है तो हम पूरा प्रोवाइड करेंगे ऊपर से।
हम फिर देखेंगे कि फिक्स सपोर्ट बेंडिंग मोमेंट कितना है, उस हिसाब से प्रोवाइड करें। हो सकता है कि वो उससे ज्यादा हो।
ओके सर।
सर
प्लीज
सर ये जो हमने नेगेटिव बेंडिंग मूवमेंट प्रोवाइड, नेगेटिव रिइंफोर्समेंट प्रोवाइड की है सर, सर ये जो कट यहाँ पे रखा है, तो सर इसको अगर हम नीचे की तरफ ये जो हम पॉजिटिव बेंडिंग मूवमेंट ला रहे हैं तो इसके साथ नहीं मिला सकते, या उसको एक्सटेंड कर दे नीचे वो सेक्शन ए में जो दिख रहे हैं पॉजिटिव के लिए? यस सर, इस तरह। Yes, sir.
This was a practice long ago, but this practice has been abandoned because of this breakage of steel and problems in this bending practically. So this is not done these days. Though it can be done, but from a practical point of view, it becomes very laborsome and difficult. So this is not done these days.
Okay, sir.
Okay. So now when this is clear, we will start discussing the design of girder. Here. Now, you know that the girder is supported on one end. On one end, it is supported on wall. On the other end, it is also supported on wall and intermediate two supports. It is resting on columns. Correct? And it is symmetrical about the mid span. Okay, it is symmetrical about this mid span, both sides. Okay, the span length of the girder is also around 30 feet. We'll calculate the lengths. Center to center for the first, from the center of the wall to the center of the beam is 30.75. However, center of the inner part of the wall to the center of the column. Center of the column is 30 feet. Center of the column to center of the column is 30 feet. Okay, so in order to calculate this center to center distance, 30 plus wall will be added to this, and the clear length are also calculated like this, because the length from the inner face of the wall to the center of the beam is 30 feet. So 30 minus half of the wall, half of the column shall be deducted from this. This will give us 29.25 inch real length, because column is 18 inch. And from this interior, this will be 30 minus 18 inch, because 9 inch is this column and 9 inch is this column. So 30 minus 9 minus 9. This will give us 30 minus 1.5, 28.5 feet rear length of this span. First step is again to calculate size of the girder, which is the width and the depth. Width are usually assumed 12, 15 or 18 inch, and the depth are calculated from the minimum criteria of the ACI code. But as I explained earlier in the case of beam, that it is not necessary that you exactly choose the same depth as given by the ACI code. It is always advisable to use more depth than given to us by the ACI minimum criteria. So in this case, if you look at this equation, the equations remain the same. there is no difference from the design point of view in a girder and in a beam. Between a girder and a beam, there is no difference. There is no difference from the design point of view. From the terminology point of view, we will call a beam a girder when it supports one or two more beams. Okay. The span length of this girder is almost the same as the span of the beam. So the minimum depth according to the ACI code will be almost the same as that of the beam, but we will assume the girder to be 36 inch. And again, you can ask why. You see that the minimum thickness of the girder, H minimum, is L by 18.5. L by 18.5. Okay, which is the same equation that we used in the case of beam, L by 18.5, and L is 30.75. So the depth is 15.95 inch, exactly the same as was in the case of beam. But in the case of beam, we increased this depth to 24 inch. And now in the case of girder, we are increasing this depth to 36 inch. Okay. Again, this depends on many other things beside the experience of the designer, because this girder is to support two beams whose length is almost the same as this of the girder. So this girder must be stiffer in the beam, and we can make this girder stiffer than the beam if we increase the depth of the beam. Then the question is how much? How much depth? In the beginning, if you do not know what to do, you can assume a depth slightly larger than the depth of the beam. And finally, when you check the reflection of the girder, beneath these beneath the locations where it supports the beams, you will find out that the deflection is more than the permitted deflection given by the ACI code. But in this course, once again, we are not going to discuss the deflections, or we are not going to discuss the calculation of deflection of beams. And then I mean to say that the deflections are not calculated in these lectures. If you can calculate the deflections and then compare this deflection with the permissible deflection of the ACI code, you will be able to see whether the assumed depth was correct or not. In these lectures, all these lectures, since we are not doing this because the calculation of deflection will open another area of discussion, and it is beyond the scope of this course. So we are not discussing all those deflection steps. If you are interested in the deflection calculation, again, in my MSc lectures, you can find out the serviceability lecture, and the serviceability lecture will contain all necessary steps to calculate deflections, and then the calculated deflections can be compared with the permissible deflection, and only then you will be able to see whether the assumed depth is correct or not. Here in this case, we are not doing this. So we will be doing some trials. We are assuming a depth of 36 inch in this case, okay, based on our experience, and because I know that 36 inch deep girder will be able to support the load which is coming from two beams being supported by this girder. So we are assuming 36 inch deep beam, and we are now also assuming a wide girder as compared to beam, because the width of the beam was 12 inch and the width of the girder is being taken as 18 inch. Why? Because we are expecting that there will be more reinforcement in the girder, because the girder is supporting two intermediate beams. So to place, in order to accommodate the amount of reinforcement that we are expecting, we should provide wider beam, wider girder, in order to easily accommodate all the reinforcement. Okay, so 18-inch by 36-inch girder has been finally chosen for this design, for this case.
सर लेकिन ACI जो एक्सक्यूज मी सर,
हाँ जी प्लीज
सर ये ACI रिकमेंडेड जो होगा सर, डेप्थ हमारे साथ 15.9 आ रहा है और हम 36, तो सर ये तो डिफरेंस तो बहुत ज्यादा नहीं है सर?
बहुत ज्यादा है। अभी मैं आपको एक नेक्स्ट ACI कोड में इस इक्वेशन में एक इशू है। If you look at this ACI equation, so it only depends on the length. It does not depend on the weight, which is coming on the beam. आपने इस इक्वेशन पे और किया, it is L by 18.5. The equation is L by 18.5. So regardless of the weight coming on the girder, the depth will always remain the same, which is illogical. बात समझ रहे हैं आप? Because with the increase in load, the depth, what is the purpose of choosing this depth? The purpose is to choose a depth so that the deflections are controlled under the load. Okay?
Okay, sir.
And you know that delta, which is the deflection at the midspan, will keep on increasing with the increase in load as well. Okay, not only with the length. It is obvious that delta will increase with the increase in length, but it will also increase with the increase in load, W. But in order to simplify the equation, the ACI code has omitted the load part and only included the length part. But there is a disadvantage to this simple equation. And the disadvantage is that it does not contain the load part. So regardless of the load coming on a girder, if lengths for a beam, if there are two identical beams, one having a weight of, let's say, 50 kip per foot, one subjected to a weight of 50 kip per foot, and the other subjected to a weight of just 1 kip per foot, the depth according to the ACI code equation will remain the same. So this is one of the disadvantages of the ACI code equation. There are some other codes like New Zealand codes and Australian codes. They in their codes, they have given a very comprehensive equation which also takes into account the load part of the load to which the member is subjected. Okay. However, in the current versions of the ACI code, in this simplified equations, there is no load to be considered in the calculation of depth of the beam. As I said earlier, this is a simple approach to assuming depth of the beam. In the detailed approach and in the routine design practice that we do in our design projects, what we do is that in the beginning we assume a depth, since we are designing beams regularly on a daily basis, so we know what depth is required for a particular span length of the beam. However, if we do some mistake, even in the assumption of the depth of the beam, finally the deflections are calculated, and if the deflections are not within the permissible limits, then we increase the depth. So with one or two trials, then we select the correct depth. Okay. But in this case, because you see that in the first course, you learn few things about the design. In this second course, you will learn few things about the design, and so on. Slowly and gradually, you will keep on, and finally, there will be a complete holistic approach wherein you will be using that approach to design a particular project. Otherwise, if we start discussing all these aspects, different aspects of the design of a beam, then only beam, I think we will not be able to design a simple beam, because all the aspects cannot be covered in one course or one lecture. Okay, so at the moment we will just take this for granted that we are assuming a 36-inch deep beam for some reason, and the reason that I explained earlier is the controlling deflection, control of deflection. Okay, we will be trying to control deflection because this girder is taking load from two beams, okay, which are 60 feet, otherwise 60 feet long beams. But these 60 feet long beams have been divided into two parts, 30 feet. Why? Because the girder is supporting these two beams. If the girder is not supporting these two beams, and the beam is itself 60 feet long beam. Now, there is an animation where you will be able to see if we select the ACI minimum depth for this girder, then the girder will not be capable of resisting the downward deflection of the beam at the location where the beam is supported on girder. Because you should remember that we are providing this girder in order to reduce the length of the beam. The length of the beam is 60 feet, and we want to reduce the span length of the beam to 30 feet. Okay, and this we can do if we provide a support at the midspan of the beam. The support can be provided in two ways. Either we provide a column or we provide another beam to support this. The column is very obvious because column will, if column is provided beneath the beam will be perfectly divided into two spans, and every beam will deflect, and the center part of the point where the beam is supported on a column cannot deflect. This you can imagine very easily. However, if another beam is provided, then if that beam is not stiff, then the beam and the girder, both, they will come down, and the beam which has been provided to minimize the deflection of the 60 feet long beam at that location where another beam has been provided will not be successful. I will show you this through video in the next slide. Look at this animation now. These are the location where this location, the beam is supported on columns. This is support which is assumed to be a column, and this is support to be acting as a girder. You can see that the girder and the beam, they are acting downward, while the column cannot come down. Okay. So if this girder is very weak, then this shape of the negative bending moment will not be possible, and the whole beam will come down. Okay. I'll show this video once again. You can see in the deflected shape. So for this reason, we have chosen a 36-inch deep girder. If we further decrease the depth of this girder, then this part, which is a curvature up, this curvature up means that negative bending moment is developed here, and some kind of resistance is offered by the girder to the beam in order to minimize the deflection of the beam at this point. So if this is not done, then this whole point will come down, and this will be like this. Deflected shape will be like this. Okay, can you see this cursor now? Okay, can you see this?
No, sir.
Okay, like this. I mean to say that if this location, at this location, what is happening at this location? Okay, there is a girder here, so you can see that there is a curvature up like this. Okay, if the girder depth is small, or in other words, if the girder is not stiff, so the girder will not be capable of keeping beam at its location here, at this location, not minimizing the deflection of the beam at this location. So this elastic curve can come like this, because the beam and the girder both will come down. In order to keep this up, you have to provide a deep girder here, because this is resting. The beam is being rested by this girder, which is this girder, and this is the beam. The beam is coming like this on this. So at this location, where the beam is supported by the girder must be stiff enough to minimize the deflection of the beam at this location. Okay. Okay, next coming to the loads, how the loads are calculated. As we have seen in the previous slide, that the girder will be loaded by beams with the point loads PP, and then its self weight in some part of the slab, this part of the slab which is directly resting on the girder. Okay. So the two reactions which are coming from the shear force diagram here, they are 40.5 into 281 kip. So this 81 kip reaction will be placed as a point load on the girder. Kip. And the self weight of the girder is 36 by 18. So 6 inch is coming within the slab. So the hanging part is 30 into 18 into 0.15 into 1.2 divided by 144 is 0.675 kip per foot. Okay. And small part of the slab which is coming on the girder directly, this part is 0.214 into 18 divided by 12 is 0.321 kip per foot. Okay. And this will be done, the slab part, this slab part, this step will be necessary only in the case where the loads, the analysis has been done based on the clear lengths. If the analysis is being done based on the center to center length, then this step is not required. This step is not required. Okay, because if you look at the beam analysis is being done based on the clear lengths. So the point load is coming from the clear length. And clear length does not include this part, this slab part. Okay, you think on this, and if it is not clear, you can come up with a question on this next time. This will need a little bit thinking, and you think on this, discuss it among yourselves. If it is not clear, then you can discuss it with me. Anyhow, the total load on the UDL coming on the girder will be 1 kip per foot, but it is a point load 81 kip. Okay, and you know that when a member is subjected to point load, you cannot use the approximate analysis of the ACI code. You must have to use some other method of analysis, exact method of analysis. According to ACI 6.5.1 ACI approximate analysis, which is coefficient method, is subject to the following condition. The structure is 2 or more spans. The spans are approximately equal, and loads are uniformly distributed. So in this case, loads are not uniformly distributed. There is a load, uniformly distributed load, but there are factor loads as well. So we cannot use the ACI approximate equations for this. We have to analyze this. You can use any method of analysis that you learned in your analysis courses, stiffness, flexibility, anything. After we do analysis, we finally come up with this shear force and bending moment diagram. Again, I will ask you to draw the shear force and bending moment diagram carefully in your notes, and then also start the designing of this girder only for flexure. Okay, I will quickly discuss with you the bending moment diagram. If you look at the bending moment diagram, so in the bending moment diagram, unlike the previous cases, look at this span. The positive bending moment is not at the mid span, because we have a point load here. This girder is not subjected to uniformly distributed load. So you have a maximum positive bending moment at 10 feet from the face of the support here, 10 feet from the center of the support. This value is 668.5, and then it slowly and gradually reduces to a value of 424.55 kip, and then it becomes negative 731.9. Okay, central portion. In the central portion of the girder, in the central portion of this negative bending moment, again is changing to become positive bending moment, but the positive bending moment value is very, very small as compared to this value. Okay, and then it is symmetrical beyond this point. So we have to design this girder for a negative bending moment. This one, this negative bending moment and this negative bending moment are one and the same. So if you design for this negative bending, automatically you design this part, and then positive bending moment, this positive bending moment, and this positive bending moment, and these three positive bending moment, and we will adjust in the reinforcement. Okay, according to this equation. So you start doing this. I will.
Hello everyone.
Yes, sir.
हेलो एवरीवन, सर बाहर चले गए। आप ये गर्डर डिजाइन करिए फ्लेक्जर के लिए। ये जो वैल्यू गिवन है इसके इसके लिए डिजाइन करिए। अब सर कुछ देर में आएगा।
ओके सर।
ओके सर।
अगर किसी को कोई मसला हो तो पूछ सकते हैं, मैं इधर पड़ा हूँ। जी फ्लेक्चर के लिए डिजाइन हो गया। हेलो हेलो।
ये सर अभी कर रहे हैं।
अच्छा चूंकि ये बेंडिंग मोमेंट एक दूसरे से बिल्कुल मुख्तलिफ हैं, ये एक्सटीरियर पे और इंटीरियर, इस वजह से हम इसके लिए अलग डिज़ाइन करेंगे और इसके लिए अलग डिज़ाइन करेंगे। इसमें वेरिएशन बहुत ज़्यादा है ना, ये वैल्यू बहुत ज़्यादा है एज कम्पेयर टू दिस वन। तो इस पेन के लिए अलग और इस पेन के लिए अलग, ये दोनों डिज़ाइन के लिए पॉजिटिव बेंडिंग मोमेंट एक्सटीरियर और ये पॉजिटिव बेंडिंग मोमेंट इंटीरियर। और नेगेटिव बेंडिंग मोमेंट वो दोनों एक जैसे हो, तो इसके हम सिर्फ इस एक व्हील के लिए डिज़ाइन करेंगे पॉजिटिव सॉरी नेगेटिव बेंडिंग मोमेंट। इससे पहले हम बी इफेक्टिव फाइंड करेंगे और बी इफेक्टिव एसीआई के जो डिवीजन हैं वो 16 एच प्लस बी डब्ल्यू। वो स्लेब का जो थिकनेस है वो 6 इंच है और टी बीम का जो विप पार्ट है वो 18 इंच है, इस तरह। तो इससे 114 इंच और क्लियर स्पेन ऑफ गर्डन डिवाइड बाय 4 प्लस बी डब्ल्यू। वो क्लियर स्पेन है वो 29.25 डिवाइड बाय 4 मल्टीप्लाई बाय 12, क्योंकि ये फीट में 29.25 फीट, तो ये 12 के साथ मल्टीप्लाई करके ये इंच में कन्वर्ट हो जाएगा। और बी डब्ल्यू वो 18 है, तो 105.75 इंच इससे आता है। और क्लियर स्पेसिंग बिटवीन द गर्डर वो नॉट एप्लीकेबल। तो फाइनली बी इफेक्टिव वो 105.75। ये चूंकि मिनिमम है तो इस वजह से हमने ये लिए।
Okay, so I hope you can design this girder for the given bending moments very easily. If you have any question, you can ask your questions. Otherwise, we will continue the design and we will try to complete this design of flexure and shear today. Okay. So we will move ahead. I hope this flexure design is clear to all of you. Okay. Next, we will design the girder for shear. This time we are using a different approach. This is a very useful approach for the design of shear. We know that D is 33 inch, which is equal to 2.75 feet. If we calculate 5EC, which is the shear capacity of concrete, using this equation 0.752 into this thing, BD, this comes out to be 48.8 kip. And you know that 48.8 kip, this is a constant thing, and this constant shear capacity is present everywhere along the girder length. Okay, this exists because B, if B remains the same, B is 18 inch, D remains the same, strength of concrete remains the same. So this value of 48.8 kip exists everywhere along the length of the beam. Okay. Now, according to the maximum spacing criteria of the ACI code, these are 4 equations that we are using. We have been using these equations in our examples. So from this equation, S comes out to be 9.5 inch, then this D by 224 inch, 11.9 inch, and this 9.5 inch is the maximum spacing according to the ACI code. So next we will calculate 5ES given to us by this 9.5 inch spacing. Okay. We know that total 5EN is the sum of 5EC plus 5ES. 5EC we have already calculated, and 5ES, if we space our stirrups at 9.5 inch spacing, which is S max now in this equation, we know that S is equal to pi AV FYD divided by VU minus pi VC. What is this VU minus 5VC? This VU minus 5VC is basically 5ES, because we know from this equation that 5EN is equal to 5VC plus 5ES. So this is also equal to, must be greater than or equal to VU. If this is equal to VU, then VU is equal to 5VC plus 5VS, and 5VS is equal to VU minus 5VC. So this thing in the denominator is basically 5VS. 5VS. This is 5VS. So 5VS can be calculated as 5VS is 5 AVFYD divided by S from this equation. So if we space our stirrups, all the stirrups at 9.5 inch apart, 9.5 inch center to center, then the 5VS, the shear capacity of stirrups, will be equal to 22.92 kip. Okay, now 5EN, which is the combined capacity of the girder in shear half partly by concrete and partly by this stirrups will be equal to 71.72 kip. Okay. Now, if we provide stirrups at 9.5 inch center to center everywhere along the length of the girder, we will have a capacity equal to 5En 71.72 kip all along the length of the girder. Okay. So wherever VU is less than 71.72 kip, wherever VU is less than 71.72 kip, this spacing of 9.5 inch will be enough at all those locations. But wherever VU is greater than this, for that we will calculate spacing of the stirrups. So if you look at the shear force diagram, now you look at the shear force diagram, because shear force diagram has a lot of values. So it will become very difficult to calculate spacing of stirrups for each and every location, and then practically it will be almost impossible to provide stirrups with spacing, with variation in spacing in this one girder. So much variation. There will be a lot of variation if we design for this shear, for this shear, for every shear. If we keep on changing the stirrup spacing, it will become very difficult. Okay, now if you look at this, you can see the shear 71.97 kip, 61.73, 19.27, 28 point this. Okay, so this location from A to C, from A to C. Okay, and also on this, on the other side, in this location, we don't need to design this per shear. We can provide 9 inch spacing here in 9.5 and 9.5 on both ends. But if you look at from D to C, from D to C and D to E, and G to F and G to H, they are similar. They are same. This location and this location, from this, because the girder is symmetrical. So in these two locations, from D to E and G to F, the shear force values are more than this. It is 120.77 kip here, 120.77 kip. Okay, so in this D to from C to E location and from F to H location, we need some closer spacing, closer than 9.5 inch, and everywhere else we can provide 9.5 inch. So we will pick up just one value, which is 120.77 kip, and we will design for this, and we will provide the spacing from C to E and from E to H, and for the rest we will provide 9.5 inch. Okay, so C to D and D to E, we have 120.5 and 96. Critical shear is now 119, 5E CV no, so spacing comes out to be 3 inch. For D to E comes out to be 4.5 inch, but finally we will select 3 inch on both sides in order to avoid too much variation in spacing. 3 inch and 3 inch spacing here, 3 inch here, 3 inch also here, and the rest 9.5 inch is okay, 9.5 inch okay. But now from practical point of view, whenever we provide closer spacing like 3.5 inch, it will not be advisable to use 9.5 inch spacing along in side by side with 3 inch. So we will reduce this 9.5 inch spacing to 6 inch. We can reduce this to 6 inch. So on this spacing, we can provide this location 6 inch and then 3 inch, then again 6 inch, 3 inch, and this. We can use the checks. If I had to design this girder in my design office, I would have provided 3 inch spacing from one end to another end, because it's the only one girder in this project, Okay, and this is one of the most important structural elements. So I will not keep on changing the stirrup spacing, and I will use only one spacing, because for this, in this one girder, if we change the stirrups for economy, we will at the end only save 5 or 6 or 10 stirrups, which in the whole project's possess no value, monetary value. I mean, that this will not give us a big saving. So, but it will simplify our work and simplify the work of the field supervisory staff. So they can, if you recommend to them that from one end to another end you provide 3 spacing center to center, so there will be very small chances of any mistake, and too much variation in spacing have a lot of chances of making mistakes. So in order to avoid chances of mistakes, we do certain such kind of simplification of our designs. Okay. This is the checks. Next is the design of column. These 2 columns are identical columns, so we can design only one of them with this 297.8, which is the reaction at the interior support of the girder. This is coming from girder. Okay, the girder reaction is basically a point load on the girder. This can be calculated from the analysis. Okay, you can design this because this is a concentrically loaded column. So from the 1% area, you assume 1% area of reinforcement, and assume the size of the column 18 by 18 inch. Calculate 5 PN. Since 5 PN is greater than PU, so 1% of the area is enough. 0.01 into 324, 3.24 square inch is the area. You use number 6 bar, so 8 number 6 bar will be enough. 8 number 6 bars. Then provide ties with the 16 dia 48 list of the column dimension. Finally, 8 number 6 bars and number 3 ties at rate of 9 centimeters, there will be enough. Okay, since next is design of footing. We have designed a footing in the previous lecture. We can design this once again without any problem. Effector load on the column and then service load on the column. If you remember in the last slide, we calculated this. Okay, this is the net bearing capacity. Weight of the fill. This is because 5 feet below the ground. So, and the footing depth initially assumed is 18 inch or 1.5 feet. Okay, clear cover is 3 inch, 1 inch the diameter of the bar. If there are 2, there must be 2 rows of reinforcement, 2 layers of reinforcement. So from the contact point between the 2, we'll calculate D. So which means that 3 inch plus 1 diameter of the bar will be deducted from the total depth of the footing. And this will come out to be 14 inch. Then next step, weight of the fill in concrete. You can do this very easily, which comes out to be 0.575. The bearing capacity, from the allowable bearing capacity 2.204, net effective bearing capacity is calculated. This comes out to be 1.629 kip per square foot. Then the area required is 234 divided by this. So area is 12 by 12 feet. Then for the reaction, for the bearing pressure, U factor load on the column divided by the area comes out to be 2.068 kip per square foot. You know all these steps now, how to calculate B naught is equal to 4 into C plus D. You can calculate this. Then you calculate VU, QU B square minus QU into C plus D. Okay, and then you calculate the pumping shear capacity 5 ECP, which is more than VU, so your assumed depth is okay. For the design of footing for flexure, you know this equation QU BK square divided by 2. So MU comes out to be 4104. And after this, you can do trials. After trials, AS comes out to be 8.42 square inch. And AS minimum is 10.0. So AS minimum is greater than this, we'll use AS minimum. Because AS minimum is calculated based on 0.005 BT average. Okay, once you do this, because you will be using this one, so if you now calculate the spacing or the number of bars, you can do this. Number 8 at 11 centimeters of maximum spacing can be used. Finally, now drafting. Drafting of the slab. This is the drafting of the slab. I will Drafting of the slab. This is M1. M1 means M1 is extended here. M1 mark, M1 mark. You have this slab has been named as S1, S1, S1. This is S2, S1, S2. The remaining are S2 because here are interior slab and this is exterior slab. The thickness of the S1 and S2 both are 6 inch. M1 mark mean bottom reinforcement 3/8 at the rate of 9 inch center to center. Okay, in both ways, because shrinkage reinforcement and main reinforcement both are the same. However, MT1 is negative reinforcement. MT1 is again 3/8 at the rate of 9 center to center at non-continuous and continuous end. You can take a section. You can take a section along the chart direction wherein you can show the reinforcement, shrinkage reinforcement, main reinforcement, and all this. There is a ACI 315 code for drafting and detailing. You can go through their details and you can find out what type of detailing they do. You can search and go through this detailing manual yourself. Okay. This is the beam drafting that we have discussed in the beam design. Okay. Negative reinforcement in top bars, positive reinforcement in the bottom bar. The only one thing that you need to understand and know is the positive reinforcement curtailment. If you look at this section CC, in section CC, you can see only 2 bars, bottom bars. 2 of these 2 bars, 4 out of these 4 bars have been curtailed. These 2 bars have been curtailed, very close to the interior support. Very close to the interior support. Very close to the interior support here. This cut and this cut. These 2 cuts. These 2 cuts. This one and this cut. They tells you, these 2 cuts tell you that the reinforcement here is 2 bars. Though wherever there are 4 bars and they are running in one layer, it is not advisable from my point of view that you do curtailment. But anyhow, just to show you that curtailment can be done and is possible, can be done in this manner, very close to this interior support, because very close to the support, positive bending moment is almost 0. The bending moment diagram will be like this. So you don't have a positive bending moment diagram, positive bending moment value in this location. You can do some curtailment here if you want. According to the ACI code, positive reinforcement cannot be curtailed more than 50%. Okay, so 2 bars must be carried from end to end. 2 interior bars can be curtailed. Okay, and the negative reinforcement can be 100% curtailed beyond this location. Okay, however, 2 bars are necessary to hold these steps. The steps have been provided at the rate of 9 center to center. This girder. Now, in the case of girder, the curtailment, if necessary, cannot be done in the manner that we have done in beams. This is the 2 layers of reinforcement have been provided in the exterior span of the girder with different curtailments from this end, because the positive reinforcement was closer to the exterior support than the interior support. So if you look at this curtailment, the curtailment is closer to the positive reinforcement. The bars in the second layer are closer, okay, than the interior support. And this exact location can be calculated from the equation of bending moment diagram. From the equation of bending moment diagram can be expressed in terms of x, and then these locations can be exactly calculated where this curtailment is required. Again, if I had to design this girder in my design office, I would have never curtailed this at this location. I would have curtailed this second layer of reinforcement, but here at this location, I would extend this support, and also to this support, and now to avoid this curtailment, odd type of curtailment, I would have extended it to this here, because I don't need it in this location because of the very small value of the bending moment. So if you take a section BB, in section BB you can see all reinforcement, all positive reinforcement. You can see all reinforcement in section BB, this. All reinforcement. You have 1, 2, 3, 4, 5, 6 plus 4, 10 bars. Okay. But section CC, you can only see 6 bars. In these 4 bars have been curtailed. Similarly, negative bars. Negative bars have been curtailed at L by 3. Okay. All 6 bars from this second layer have been curtailed. Beyond this point. Okay. These 6 bars from the bottom layer. Top reinforcement, second layer. Top reinforcement, second layer has been completely curtailed. And then 4 bars in the central portion have been curtailed, and 2 bars at the end have been continued to the ends. Okay. You can study this, and if you have a question, you can come up with your question in the next lecture. Similarly, if you look at the stirrups, so stirrups have been provided number 3 at the rate of 9 in center to center up to this location, and then in this location number 3 at the rate of 3 inch, and so on. Similarly, you have in column reinforcement. This is all about today's lecture. In the next lecture, inshallah, you will discuss some other structural options for the design of this hall. Okay, you should study this lecture, and if you have any questions, you can come up with your question in the next lecture. Still, if you have a question, you can ask a question now. Any question? Okay, any question?
No question, sir.
No question? Okay, thank you.
Assalamu alaikum, sir.
Walaikum salam. Any question?
No, sir. Thank you.
Okay, thank you. Thank you. Thank you.
Assalamu alaikum, sir.
Salam. Wa alaikum salam.